Bismillah. I am the coordinator of the Virtual Smart Structures and Dynamics Lab. You all will be interacting with our lab, our staff members for next few weeks to few months, and I take today's opportunity to introduce you how our lab should be used so that you can get maximum benefit out of here. So I have prepared a brief presentation and we'll begin this orientation with that presentation. Now this is a presentation about what we will cover today. I will give a very brief introduction about the virtual labs. Then we'll come to our specific lab, the Smart Structures and Dynamics Lab and its virtual component. We'll take you to who are the people behind this lab. Then a brief introduction to smart materials and structures. Then we'll take you a live demonstration of piezo materials and a tour of the facilities of virtual lab. And at the end, we'll give you a brief introduction to the experiments involved in the virtual lab. Of course, we'll have questions and answers after this brief introduction. Now, virtual labs, this is an initiative of the Ministry of Human Resource Development, and this project is operating under the National Mission on Education through Information, Communication and Technology. Now, we have one-point access to all the virtual labs which are covered as part of this project, and you have to just note this website www.vlabs.co.in. So it gives access to all virtual labs which may be part of any of our participating institutes. Now this virtual lab project is possible because of the association of all these institutes: IIT Delhi, IIT Bombay, IIT Kanpur, IIT Kharagpur, College of Engineering Pune, IIT Roorkee, IIT Guwahati, IIT Hyderabad, Amrita, Diyarbakir and NIT Surat. All these institutions together we are partnering with virtual labs. Now there are three types of experiments in the virtual lab. Some could be remote triggered, some could be measurement based, and some could be modeling or simulation based. Now what is a remote triggered lab? So remote triggered lab means that the physical lab exists at some central location, and this is accessible to the far user through internet. So users, they can get complete feeling of audio and visual sitting at their desktop, and they can get the data and the real-time measurements at their own convenience. So the real-time lab, it becomes a virtual lab at the PC of the student. The next type of lab is basically simulation lab. So here we have a backend which is basically a simulation engine running on a server. So here these experiments, unlike the remote triggered labs, these are not real. They are basically working on a simulation or a mathematical model. But the user gets a picture that they are sort of real experiments. Finally, we have measurement type labs or measurement type experiments. So here there is a backend, and this consists of some previous experimental data which runs on the server. But we have made it and we have provided the graphical user interface in such a manner that the user, he gets feeling that the experiments are happening in his front. Now I introduce you about the virtual smart structures and dynamics lab. Now, virtual smart structures and dynamics lab, it is a virtual extension of the Smart Structures and Dynamics Lab (VSSDL). Now, this lab was set up in 2007 by me. The aims of the lab is to carry out research towards the development of new sensors and techniques based on smart materials. That is the major aim. And we work for different areas such as structural health monitoring, biomechanics, energy harvesting, and many other interdisciplinary applications which involve structural dynamics. We have completed several PhD projects and also MTech and BTech projects. Typically, we have completed 4 PhD theses since 2007, 25 MTech projects, and 64 BTech projects. Our key research areas are the electromechanical impedance technique for structural health monitoring. We also strive to develop cost-effective variants of the EMI technique. We try to integrate EMI technique with low-frequency global dynamic techniques. We model sensor structure interaction. We perform experiments and simulations for energy harvesting, for biomechanics, and recently we have also started a new variant of the EMI technique, that is metal wire based, and we will give you more introduction for this also in today's interaction. Now, this is the virtual extension of our Smart Structures and Dynamics lab. So we have just added V before VSSDL to give it a specific acronym. Now, this lab can be accessed by this website, and you can go here directly, or you can also go here via the VLab web address that I gave you earlier. So our lab is put in use for our own coursework at IIT because the numbers of students they are increasing, and this virtual lab has given us an opportunity to use our resources with optimization. Now let me give you an introduction about the people who are involved in this lab. I am the main coordinator of this lab, and I am assisted by a creative team which look after the design of all the experiments, and then we have a maintenance and operations team. Now the creative team, this is headed by research scholar Ms. Naveen Kaur, who is the team leader, and she is assisted by Ms. Sushmita Naskar, who has just finished her MTech. So this creative team is responsible for adding new features to the existing experiments and for debugging, and all the related processes they are handled by the creative team. Now Naveen, she is about to finish her PhD work very soon. Sushmita, she has completed her MTech and she is a prospective PhD student. The maintenance and operations team is held by 3 staff members. Mr. Lal Singh, who is GLA, and he is a very senior staff member of our lab. Then we are assisted by Mr. Vijay Verma and Mr. Sujit Tandon. Mr. Vijay Verma and Mr. Sujit Tandon, they will be in touch with all the users throughout the course of the virtual lab. So basically for day-to-day basis, you will be in touch with the maintenance and operations team. So this team keeps on running all through the day to make sure that all the experiments they are available to you without any problem. Now, what is a smart material? Smart material looks like any other ordinary material, but it has a specific ability, a property, a feature. It has the ability to change its physical properties, one or more physical properties, in a specific manner when it is acted upon by a specific stimulus. So they show stimulus response characteristics. Now these are some of the smart materials, such as piezoelectric materials, electrorheological fluids, shape memory alloys, and optical fibers. Now this term smart materials, it was coined in 1988 at a US Army Research Office workshop on smart materials, structures, and mathematical issues. So it has become a very standard term since then. Now these are the smart materials and the associated direct effects, converse effects, that is all the stimulus response relations. Piezo materials, if we provide stimulus in the form of stress, we see the development of electric charge. Conversely, if we apply electric field, we see the development of mechanical strains. So these are the stimulus response features which make these piezoelectric material a smart material. Then we have shape memory alloys, where if we heat the component above a certain transition temperature, we see that the component returns back to its original memorized shape. We have electroradiological fluids, where if we provide stimulus as electric field, we see change in viscosity. Similarly, optical fibers, if we provide stimulus in form of temperature, pressure or strain, we see changes in the optoelectronic signals. Finally, magnetostrictive materials, where magnetic field it acts as a stimulus and it results in mechanical strain. There may be few more smart materials, but essentially the smart feature is that they show stimulus response characteristics. Now, if you want to learn more about smart materials, then you go to our web page and look for this video. Now, in this video, we have given detailed information or detailed videos with animations how each smart material behaves. So this will be interesting to you. I am not showing these videos today for lack of time. Now let's just see briefly about piezo materials. Now piezo materials, they are smart because if we apply mechanical stress, we see the development of charges, like this is shown by this animation. Conversely, we apply electric field, we see the development of mechanical strain. So these are the smart features. They are like any other ordinary material. They obey Hooke's law, that is if we apply stress, we see the development of strain. And the two are proportional. What is additional in the case of the piezo materials is that when we apply an electric field also contributes to strain development. Hence, the total strain is made up of two parts, one because of the direct stress and the other because of the electric field. And the two terms, they are added to give the final strain. Similarly, piezo materials, they are like any other ordinary dielectric material. In any ordinary dielectric material, if we apply an electric field, what we see is the development of charges. What is unique in piezo materials is that if we apply stress, then stress also gives rise to charges. So here the total charge density becomes a summation of the two charge densities resulting from electric field and stress. The unique characteristic of the piezo materials is that in both the direct and converse effects, this is the direct effect and this is the converse effect. The constant which relates the two fields, that is one field is the stress strain field and the other is the electric field. The constant remains exactly the same, D31. So why we call it D31? This is called as piezoelectric strain coefficient. So 3 implies that 3 is the direction of the electric field and 1 implies that 1 is the direction in which stresses and strains they are measured. Similarly, we have other constants like D32 and D33. Now, this is the equation for sensing applications. This is used for sensing stress or strain. So, for that purpose, we have very easy use. We have to cut any external electric field supply. The equation becomes very simple, and what we can derive using parallel plate capacitor theory, we can derive a direct relation between the voltage generated and the strain. So this is how we use the piezo materials for sensing strains. So the typical sensitivity of the piezo materials is something around 200 millivolts per microstrain. Now piezo materials, they are very rugged, they can undergo very large strains. Typically they show linearity up to 6,000 microstrains. And they can undergo very large strains even up to something around 10,000 microstrains. Now this is a typical response of a cantilever beam where a piezo patch is bonded. and this is like a free damped oscillations. You can see here the high quality of the response, and this is the fast Fourier transform of the same previous signal. So when we do the fast Fourier transform, we get into the frequency domain, and peak of the fast Fourier response basically tells us the natural frequency of the signal. Basically, this the value is basically the component of the different the addition or contribution of the different frequencies in the voltage. Now there are possible applications of piezo materials. They can be used as sensors, I have just shown. They can be used as actuators, and they can also be used as both sensors and actuators together. Now this technique is called as the electromechanical impedance technique, and it operates in high frequency of typically several hundreds of kilohertz. So in this technique, we bond a piezo material on the structure. Now when we have bonded the piezo material on the structure also becomes smart. We'll see the formal definition of smart structures later. So we have to excite the patch starts interacting with the structure dynamically, and this interaction leads to the transmission of stresses and strain from the patch to the structure and vice versa. So here the vibrating patch influences the dynamics of the structure, and the dynamics of the structure in turn influences the dynamics of the patch, and hence the electrical circuit comprising of the piezo patch and the exciter. So that is the main basis of the electromechanical impedance technique. So here what we do, we connect the piezo patch to an LCR meter and do this kind of excitation, and by this we do a frequency sweep and we get this kind of unique signature of the piezo patch. This unique signature is like a thumb impression of the structure. It will not change as long as the structure is same. So here the electrical circuit comprising of the patch, that is taken care of. So the electrical admittance or the electromechanical admittance, this carries the properties or the dynamic characteristics of the structure. For example, you see here the peaks. All these peaks basically they are some sort of resonance frequencies associated with the structure. Although it may appear that the quantity is electrical in nature, however, it has the mechanical component. That's why we call it as electromechanical signature. So admittance has two components. One is the conductance and the other is the susceptance. So conductance shows the features of the structure more sharply. So typically the main use of the EMI technique is in damage reduction. If there is any damage in the structure, even if it is very small in nature, the signature of the patch, that is its thumb impression, will change, and this gives us the complete indication of the occurrence of damage. Now we come to smart structures. So smart structure is something like if we add a piezo material on structure and then we try to use it for some purpose, say for vibration control, sensing, health monitoring, then the structure becomes smart. Formally, Ahmed has defined smart structure as follows. It is a system or structure which has built-in or intrinsic sensors, actuators and control mechanism. So these are the three components: sensors, actuators and control mechanism. So it's not necessary that both sensors and actuators should be there. If only sensors are there, they also make it smart. Now all these components, what they contribute, they make the structure capable of sensing a stimulus, responding to it in a predetermined manner and extent in a short appropriate time, and reverting to its original state as soon as the stimulus is removed. So this is the definition of the smart structure. Now some of you would be also taking part in the online course on smart materials and structures. So I advise that as far as possible, please take part in this course also. This will increase your understanding. I am just outlining the contents of the course for your benefit. So course has 50 lectures. The first is introduction, Second, will introduce you to the concept of smart materials and structures. Third is basically on piezo materials. Fourth is continuation of the third, theory and applications. Fifth and sixth will be on fiber optic materials, theory and applications. Seventh on shape memory alloys. Eighth on smart materials for structural health monitoring. 8th, 9th and 10th will continue in structural health monitoring. 11th will be on biomechanics. 12th on vibration control. 13th and 14th on energy harvesting. These two lectures will be taken by Naveen. So lectures 13, 14 and 15 they will be very interesting. 13th and 14th lecture will be delivered by Naveen, who is an expert in the area of energy harvesting, and she has done most of her work on PhD and is currently writing her thesis. And lecture 15 will be delivered by Srishita, who has completed her MTech project and secured her MTech degree in the area of smart materials, especially the piezo material, the metal values, EMI technique. So you will find these lectures very interesting because you will see a lot of practical applications to the lab. Now what we are planning is that we will give you a live demonstration of the piezo materials in our lab. We take you around the lab, we show various facilities, how a piezo patch really looks like, how it works, what kind of signal it gives. So I am just about to stop here, and after we finish the live demonstration of the piezo materials, we will take you to our virtual lab. We have the central cabin where we have all the equipment. We will take you a tour of the various equipment and the cameras. And after that, we'll come back again in the presentation mode. We'll give you a brief introduction to the experiments of the virtual lab, and then we'll have questions and answers. So we have planned this session to show you some of the features of our smart structures and dynamics lab. So we begin with a very fundamental feature, a cantilever beam with piezo patch, how a smart structure looks like. So we are now focusing the camera on the actual experiment. Do you see cantilever beam? And this cantilever beam, we have one piezo patch. We are now zooming the camera on the piezo patch. So this piezo patch is permanently bonded on this structure. So this structure becomes smart. Now how this piezo patch helps, it provides the signals. When the structure is vibrating, now we will just vibrate the structure and you can see the signal in the oscilloscope. So if we vibrate the structure, what we see is the development of charges in the piezo patch. Maybe you can excite again, yes, and then we stop. Yeah. Now we zoom here and show you how the signal looks like. Now if you see here the signal, this is like an oscillating signal. So here you can see the voltage is changing from positive to negative and continuously going in this cycle. So essentially the vibrations of the piezo patch, they are very well captured. Rather, the vibrations of the structure are very well captured by the piezo patch. So now the structure becomes smart because it is sending the state of the structure and which user can make use. Now after this, we will take you to one experiment involving energy harvesting. Now we take you to a small wind tunnel experiment where we demonstrate you how piezo patches they can be used for harvesting wind energy. Now we are taking you to our setup. Now this is our setup. You can see where there is a small wind tunnel and we have a fan at one end, and then we also have a cantilever beam with a piezo patch on the top. Now wind is free everywhere. If we can harvest wind energy, if we can convert it into electrical energy by using the piezo patch as a generator. Now this is a maintenance-free generator like the conventional tan mount. So it does not require any maintenance. It can go on for years and years. So we just demonstrate you how we can generate a power. So Sushmita is now going to switch on the fan, and you all can focus towards the oscilloscope. Now, as the fan is being switched on, you can see that the cantilever is fluttering, and as the cantilever is fluttering, the piezo patch is undergoing strain reversal, and hence it's generating alternate electrical voltage. This can be stored in any suitable battery, and this can be used later. So this is how we can generate meaningful energy from wind by using the simple piezo materials. Now the fan is switched off, again the vibrations they have died down. So this experiment illustrated you about the energy harvesting potential of piezo patches. Now after this, we will take you to the section of our lab where we have the virtual lab equipment.
Hello everyone, I am Sushmita. I completed my MTech from Smart Structures and Dynamics Lab from IIT Delhi, and now I will take you a quick tour of our lab. And before performing any experiments, it is emphasized to go through the links which has been given in our website so that you can have a brief idea of the concepts, and you can see the manuals of the experiments too. Firstly, I will show you the experiment number 1. This is the cantilever beam, and the PZT has been attached at the end of this cantilever beam. And the main aim of this experiment is to find out the natural frequency. And if you will, and this mic is here to get the sound of you can hear the sound, and you can see the total experiment when you will perform the experiment. And this PZT has been connected with the digital multimeter, and it will be connected with the vPro software via user's computer. This is the digital multimeter, and the total experimental setup can be seen from this camera, and you can see the total setup when you will perform the experiment. And now I will tell about the experiment number 2, that is the aluminium bar, and it is freely suspended with the help of this flexible tape. And if you will see this aluminium bar, there is 2 PZT patch which has been attached. This is the PZT patch which is attached at the top of the beam, and this is the bottom of the beam. This 2 PZT patch has been attached parallelly to get the axial mode of this beam. And this one is connected with the help of this LCM meter. LCM meter is an impedance analyzer which we are using for the EMI technique, where we will be calculating the conductance and susceptance signature via vPro software from the user's account. And this is the camera which is capturing the whole setup when you will perform the experiment manually. And this is the experiment number 3 setup. This is a 3.2 meter steel beam where PZT patch has been attached, and this PZT patch has been connected with the DMM, digital multimeter, and this digital multimeter will be connected with the vPro software via the user's account. And this one is connected with the function generator, and function generator, from here we will get the electrical form with the sine wave at the sweep form, and this is connected with the this amplifier. This amplifier will amplify the electrical power, and it will give the power to the shaker which is connected at the bottom flange of the beam, and this will convert it to the mechanical charge. And now if we will give the output from this function generator, at the resonance frequency we will have a snoring sound. Now I will tell you about lastly about the experiment number 4, This is based on the photogeometry. That's a new technique. From here we can get the load versus deflection curve from the camera. This is the camera which will be capturing the image. This is the distance between A and B, which is known, that is 100 meter, and we have to calculate this distance of C to A and B. And this is the beam where first of all we will calculate the load deflection curve from no load condition, and then simultaneously we will be plotting the loads, and then we can get the load deflection curve and how it is variating with the loads. We can calculate that. And these four are mainly the trigger based experiments. There are more four simulation based experiments also, which you can perform from our experimental from our website. I'm giving you a brief description of my MTech project, that is on a metal wire based variant of EMI technique, and I completed my MTech work on this particular topic. This is the specimen on which my main work was there. This is the 1200 into 970 millimeter metal steel plate where the PZT has been attached manually, that is conventionally, on the host structure, and also it has been attached in this metal wire also, and the wave propagate on this way. There are three types of damage: damage 1, damage 2 and damage 3. 3 damage I have been induced, and then I calculated with the help of this conventional one, and this is the metal wire. The main advantage of the metal wire technique is we don't need to attach the PCT on the host structure. We can easily detect the damage with the help of this metal wire technique, and this metal wire technique is giving a very good result from the other variants also. So we are looking forward to work on it on the concrete structure and on the some other several projects also. Thank you.
Okay, welcome back now. Now this is the website of our virtual smart success and dynamics lab. Now here we have all essential videos. They will be shown to you at the beginning of each session. We have passed the instructions to your instructors how to conduct the virtual lab and sequence of the experiments. So all these videos you can use, and from time to time these videos will be shown to you all. Now here in our website you can see that there are two types of experiments. The first type is trigger based experiments, where we have experiments 1, 2, 3 and 4. And the other type are the simulation based, 5th, 6th, 7th and 8th. In fact, experiment number 7 is the measurement type, however we have just classified it as simulation type. So we go to experiment number 1. So each experiment, it has a video link. So if you start this video, it will take you to the YouTube link where you can listen how the experiment is to be performed. So this will give you entire picture of how to conduct the experiment. We have done this for each and every experiment. Short 5 to 10 minutes video, they demonstrate you everything. So if you go through these videos, everything will be very clear to you. So here, for example, in this particular video, we have explained about experiment number 1, how the experiment number 1 works. So after you watch the video, what you can do is you can go to the manuals. Each experiment has manual, so you can read the manual of the experiment where there is a theory and also brief references are given. What is the objective of the experiment, how to perform the experiment, how to do post-processing. All the resources and also supplementary resources have been given. After you have understood this, then you would like to see in real time how the experiment works. So you have a camera at your disposal, so you just open this camera. It will ask for username and password. You have to give it both guest as the username and guest as the password. Now this is capturing here the picture of the first experiment. Now we advise that you better use Internet Explorer for the camera. You get better control if you use Internet Explorer. So after you have physically seen the experiment, you will hear, if you put on your earphone, we have a mic here. So this mic basically captures the ticking sound, and you will get a real-time feeling that the experiment is happening in front of you. In the tour of the virtual labs corner, you must have seen and you must have heard a ticking sound. So that sound was from this one. So after you are through with all these, then what we advise you, you go through the software and install them. Now VPro 9.32 for 1 month is free, and you can install it, and within 1 month you can complete your experiments. You should also install IO library suite and IVI driver in your computer. And then before doing the experiment, take pre-experiment quiz. This will let you know how prepared you are. So after you have finished the pre-experiment quiz, and if you are fully ready, then you perform the experiment, and this will require the same software. So when you click here, you can see here VPro graphical user interface will open. So from this user interface, you have to choose a sampling interval. We recommend you to choose 1 millisecond, and then the number of readings. We advise you that you can choose 5,000 readings. That is the measurement runs for 5 seconds. Now here you can choose some file name to store, and here you can choose some directory where you want to store your file. So I am choosing here D directory. And if you want to now trigger the experiment, you can trigger the experiment from anywhere in the world. You all have to do is now press this button. Now when you press this button, it will ask you where to again verify where to save the file, and you can save it. And when you save it, the experiment is now happening, data is being collected, and very soon you will see here the output. So this is now the output here. Now do you see here the oscillations of the cantilever beam? This is the time domain, and you can also go to the frequency domain. So by the frequency domain, you can get the peak. So this peak is basically the natural frequency of the beam. It's nearly around 18 hertz. That is the natural frequency. So this data is stored in your computer. So once you go back to your computer, you see this data and follow the instructions in the manual and do your calculations. After this, you can take the post-experiment quiz questions. So that completes experiment number 1. Now we go to experiment number 2. Experiment number 1, if you have installed all the software, you need not install all again. Only you need to install IVI driver, which is a different one. But make sure that this IVI driver should be compatible with your Windows. If your Windows is 32-bit, then install the 32-bit driver. If your Windows is 64-bit, then you install 64-bit driver. Now here again we have the manual of the experiment. So here we have essentially a beam in the free conditions, and this beam is basically excited by 2 piezo patches, one on the front and the other on the back. So it excites in the axial mode. So if you want to now read the manual, click here and understand everything. So the manual is a PDF manual, you can save it on your computers, and after you understand the experiment, then you can see how the experiment looks like. So click here to get access to the camera. The username is guest and password is also guest, though I am using the administrator one. So camera opens and you can see the real setup also in front of your eyes. Please bear with it if it takes a little bit time. So after you have seen the real experimental setup, you can then go on and you can then perform the experiment. So again, it's VPro based, so here the graphical user interface will open, And here you can choose your frequency interval. This is using the electromechanical impedance technique. So you choose your frequency interval. These are the suggested values. And if you click here, so the process starts. You can change your file or destination file by clicking here if you want. So this is a real-time measurement where the data is being collected and stored in a real fashion. You can go to your directory and you can retrieve your file. So what we observe here is a peak, and this is one of the natural frequencies of the beam in the axial mode. Now the manual gives you a formula how to compute these natural frequencies theoretically, and the objective of the experiment is to compare the theoretical and the experimental natural frequencies. So you see here this peak, this is conductance, this is susceptance, so the peak frequency you can very easily know from here. Experiment number 3, please just bear with me when I switch on the shaker. Now I have switched on the shaker and I am now putting the mic in front of shaker. You will hear a snoring sound. So I hope you heard the snoring sound. So this experiment is happening with the help of this shaker. This shaker is basically exciting the beam to undergo vibrations, and the vibrations are captured by a piezo patch. So I am now performing the experiment. So these are the suggested time durations and the sampling interval. Experiment is happening now. Now we take you to experiment number 4. So this is photogrammetry experiment where we take two images and we use these two images to measure the deflection of point C. So it basically uses a very simple concept that when we take a picture, then we calibrate the distance appearing on the picture with the actual distance of 100 mm. So by using this we can calculate the distance between the points A and C. A is always stationary and C is the moving frame. Now after you put the loads, C will again get displaced. So again you can calculate or measure the distance between A and C. So by this two measurements you can always find out how much point C has displaced. So this is a very simple experiment. So you can go through the manual of the experiment and read the theory. All it requires is just the calibration of the distance. This 100 mm, you take this picture, after capturing the picture you take it on the Microsoft Word and measure how many millimeters correspond to, or how many millimeters on the Word they correspond to 100 actual millimeters. So that will be your conversion factor. And for this we have the same camera as experiment number 1. So all you have to do is use Microsoft Explorer in place of Chrome, and you can then capture the picture. You can save the picture on your computer. So every 1 hour interval what we are doing is we are adding more and more weights. So when we keep on adding more and more weights, this beam will deflect down. So C will continuously move. So you have to use your images to determine by how much amount C has deflected down. So just by using the unitary method, so you can capture this picture, save it in your computer, then transfer it to Paint or Word, and you measure what distance you are getting there. So for example, if you are getting 20 mm, that means 20 mm on the picture, they correspond to 100 mm. So like this you can establish the calibration. So after this we have the simulation type experiments. We just take you there. Experiment number 5, it is basically for beginners. It teaches about the modes of vibrations of simply supported beams. So if you input here some realistic values, say length of the beam is 5 meters, and you can enter the cross-sectional area of the beam and the moment of inertia, or alternatively you can enter the width and the depth of the beam. And here you can enter the density and Young's modulus. And then you can calculate the natural frequencies. So the frequency comes here, and this is the mode shape. Similarly, you can calculate the second natural frequency, and like that you can do this. After that, there is a small exercise where you take different values of the length, and then you sort of plot how the frequency changes with length. And then there is a parametric study, again the effect of Young's modulus on the frequency. So you can do these exercises. So this experiment is for beginners. Experiment number 6 takes the user to the modes of vibration of 2D plates. Now every experiment has a video link, so you can of course use the video link. So here you can enter the length of the plate. I am just entering some hypothetical values. Poisson's ratio. And Young's modulus. And here which mode you want. So when you do calculate, press the button of calculation, you see here the mode shape and the corresponding frequency. And you can change, go to higher modes and still higher, and you can calculate the corresponding frequencies also. Then there is an exercise for the user, a parametric study kind of exercise which you can do. Now we go to experiment number 7. So this is a measurement type experiment, and here we are just simulating the electromechanical impedance technique. So here you can always require signature. So this is based on measurement data, but for user it appears that this is like a real-time measurement. So here I enter the starting and the end frequency, and I submit here. So now this is acquiring the signature very much like in the case of experiment number 2, but the difference is that here experiment is not happening in the real time. This is a measurement data from some earlier experiment. So after you finish the measurement, you can save the data, and then what you can do is you can induce damage in the structure. For example, we have several options for inducing damage. You can induce incipient or small level damage, moderate damage, and severe damage. And for each case, you can again acquire the signature. After the signature is acquired, you can do comparison with the original baseline signature. So this illustrates how the electromechanical impedance technique is used for damage detection. Experiment number 8 is illustrating you the modes of vibration of a typical cable state bridge, and then there is a related video here which tells you about this experiment. And also we have some more videos. When you perform this experiment in your lab, your instructor will show you video of the Tacoma-Narrows bridge, which is the famous cable stayed bridge which had fallen. So here if you click here, you can see here the modes of vibration of the bridge. All you have to do is find out which of these modes is the closest to the Tacoma Narrows bridge which I fit.